I'm Swapnil sir, and today I'm here with one of the previous year question from CSIR NET exam. Solved question paper. So I already uploaded plenty of the videos on different subject like linear algebra, calculus operation, group theory, ring theory, and so many subjects. So if you wanted to check this video, you may check it into my playlist. So in my today's video, we'll go through one of the question from real analysis, which is based on convergent divergent of the series. Now let's get started on today's question. First of all, I'm gonna explain to you all the question, and then we'll move for the detailed understanding of solution. In our question, we have given a and b the sequence, which is the sequence of a real number which satisfy series n is equal to 1 to infinity modulus of an minus an minus 1, which is smaller than infinity, which strictly less infinity. Then we have to find out the series n is equal to 0 to infinity an x raised to n, and x is from real number which is a convergent or not. Okay, so that convergence we have to check for in our options are given 4 options. We have to check this conversion with respect to these 4 options. So our first option it says that x belongs to R, which is convergent nowhere in R. Okay, that is sequence an is not nowhere convergent in over R. Okay, second option is that it is everywhere convergent on R. Third option it says that on some set containing -1 to 1 that our sequence is convergent. And fourth option it says that our sequence it is convergent only on the interval of open interval 1 -1. Okay, that means we have to check whether our series which is convergent or not. Okay, so here it is the series given. We have to check whether it is convergent or not. Okay, and if it is convergent, then what point it is convergent, and it is divergent, then for what point it is divergent. Okay, now to find first option, we have to find out the point. Okay, where that point our series convergent. Okay, that means its first option it says that series is nowhere convergent. Nowhere convergent means that they wanted to say that that series it is never convergent or nowhere convergent or nowhere convergent in R. Okay, but let's find out the point where that series is convergent. Okay, and find out this take some counter series that can satisfy the properties, take some element from real, and find out whether it is convergent or not. Okay, so let's get started with today's solution. For example, for first option, that our series they say that it is nowhere convergent on R. Okay, now let's consider an. So let's consider an is 1 by n. Okay, let's consider an is 1 by n and an minus 1. Okay, so if an is 1 by n, then how we'll get the n minus 1? An minus is 1 upon n minus 1. Okay, replace n by n, then n minus 1 by n minus 1. Now let's verify this series an, can it hold the property that we have here, n is equal to 1 to infinity an minus 1 is smaller than infinity. Now let's verify, then we'll prove whether it is convergent or divergent on R. Okay, so here write here that series can we say that it is smaller than infinity or not. Okay, so here n is equal to 1 to infinity modulus of an is here 1 upon n minus an minus 1 upon n minus 1. Okay, and we have to check whether it is smaller than infinity or not. Okay, so n is running from 1 to infinity. We know that 1 upon n is a smaller term, okay, than 1. When n goes to infinity, 1 upon n goes to 0. 1 upon n minus 1 it is also goes to 0. So these terms are smaller. Surely we say that these are the finite terms. Okay, these are the finite terms. So our first property, that sequence an of a real number which satisfy this property, it hold here. So if it is hold over here, then we have to find out whether this series n is equal to 0 to infinity is convergent on R or not. Okay, so what we will get the series then, n which is equal to 0 to infinity. Okay, so an is here 1 upon n into x raised to n as it is. Okay, 1 upon n x raised to n, and x belongs to real number. Okay, and we have to check whether it is convergent or divergent. Okay, now if x is from real number, so can I select x is -1? Yeah, -1 belongs to real number. So if I select x is a -1 from real number, then we'll figure it out whether this series is convergent or divergent. Okay, so they say that the series everywhere are divergent. That means nowhere convergent on R. But we have to find out the some certain point where that series is convergent. Okay, so I found the x is a -1. Then put x is a -1. What we will get? The -1 raised to n upon n, and n running from 0 to infinity. Okay, n running from 0 to infinity, -1 raised to n upon n. Can we say that this series is convergent or divergent? What about for this series? Is it convergent or divergent? So it seems like that this series, which is some special type of series, like a alternating series. Okay, and when we have alternating series in a real analysis, then we apply Leibniz test for series of alternating convergent test. Okay, so what is the Leibniz test for series of alternating convergent test? It says that when we have series like a u1 minus u2 plus u3 minus so on. Okay, so that means plus minus plus minus. This is alternating series. Okay, and one more condition here: u1 need to be bigger than u2, u2 need to be bigger than u3, and so on. Okay, if this condition hold, and last condition, limit as n tends to infinity, un need to be a 0. If these two conditions hold, then we say that by using a Leibniz test of alternating series of convergence, we say that un is a convergent. Okay, now here we can see that if we apply limit n tends to infinity, okay, n tends to infinity, that means n goes to infinity, that means 1 upon infinity it goes to 0. That means this term hold here. Okay, that means limit n tends to infinity, -1 raised to n upon n, it goes to 0. Okay, this term hold here. Can we say that second term is more smaller than first term? So let's verify. Okay, how the term it could look like. Okay, so the term it's coming from, it is 1 to infinity, not a 0. Okay, it is 1 to infinity given in question. So here we can write the series as -1 raised to 1. Okay, so -1 upon n. Okay, so n it is also 1. Okay, -1 upon n, 1 plus -1 upon 2, -1 square upon 2, -1 cube upon 2, and 3, -1 cube upon 3, and plus 1. Okay, so what we will get? -1 plus 1 by 2, -1 by 3, and plus 1. Okay, so here we can see that minus plus minus plus, this is the alternating series. Can we say that second term u1 is bigger than u2? Can we write this way? Okay, now we can write this series as 0 plus. Okay, first term need to be a positive because first term is positive here, that's why I taken 0 first. No positive, no negative. Okay, so 0 plus -1. Okay, so what we see here, first term is bigger, second smaller, third term is bigger, fourth is smaller, and this way is goes like this. Okay, so second condition also hold here. So u1 is bigger than u2, u2 is bigger than u3, and so on. So by using Leibniz test for alternating convergence series, we say that the series an is convergent. Okay, an is convergent, but it says that our series nowhere convergent on R. So how it is possible? So it seems like that option first is wrong over here. So for your better understanding, you may see my solution for first option. Okay, so option A, -1 raised to n upon n, it is convergent. Okay, by using Leibniz test for alternating convergence series. Okay, so option A discarded, but option B, it says that it is convergent everywhere on R, everywhere. Okay, so what happen if I select x, instead of x is a -1, x is 1 only? Okay, so x is 1, take it, x is 1 in our series, what we will get then? Okay, so x is 1, then we have series n running from 0 to infinity, 1 upon n into x raised to n. Okay, we consider this series here. Okay, and this is that it is everywhere convergent on R. Okay, so take x is equal to 1. Okay, and 1 is surely it is belongs to real number. Okay, 1 it is from real number. So put x is 1 over here, so 1 raised to n is a 1 only. Okay, series n running from 0 to infinity, 1 upon n. Okay, so I got the series over here for x is equal to 1. So tell me, is it convergent or divergent series? So it is not alternating series. Okay, we cannot apply Leibniz test now. Okay, but we can apply a mod p test for convergence of a series. Okay, and mod p test says that when we have series n raised to p and p bigger than 1, then and p smaller than 1. Okay, p, whenever p bigger than 1, the series is convergent. Okay, it goes to infinity, means 0. And whenever p is 1 or smaller than 1, series is divergent. Okay, so we can see that n is equal to 1 here, so p is equal to 1. So if I got the p is equal to 1, then we say that series is 1 or smaller than 1, p is 1 or smaller than 1, then series is divergent. Okay, so our option number second also discarded over here. So what it says, that it says that everywhere convergent on R, so option number second is also wrong. Now third option, it says that on some set containing negative 1 1. Okay, there is a some set we will get in a negative 1 to 1. Yes, surely we'll get. Okay, so negative 1 is the point where series is convergent. Okay, there are some certain amount of a point which lies in this set. Our set is convergent there. Okay, but only on negative 1 1 it is not possible. Outside there are some other point. Okay, outside the point which is here negative 1, negative 1 does not belongs to that set. Okay, negative 1 does not belongs to that set. So by using the option here, option B. Okay, option B, I found the point x is equal to -1 where is the set convergent, but it says that only on -1 1. Okay, but this set does not belongs to -1. Okay, this set does not belongs to -1, so -1 is not belongs to there. So but they say that the only set of -1 1. Okay, and we have series convergent at -1, so option number 4 is also discarded. Now let us verify third option, we'll see in detail. Okay, now let us take some counter example. As we know that the radius of convergence in a real analysis, we take radius of convergence 1 upon r is equal to limit as n tends to infinity modulus of an plus 1 upon modulus of an. Okay, this is the series of radius of convergence we take in our real analysis. We'll take the radius of convergence for our series and we will verify whether which interval our series is convergent or divergent. Okay, so an, if I select is a 1 upon n, then an plus 1, what we will get? 1 upon n plus 1. Okay, now substitute these values over here. Let's verify. We will get the convergence of a radius of convergence. So 1 upon r, which is equal to limit as n tends to infinity an plus 1, 1 upon n plus 1 upon an 1 upon n. Okay, okay, so here let's go for further. Apply limit as n tends to infinity. So we'll get the denominator of a denominator is numerator, so n upon n plus 1 limit as n tends to infinity. Okay, so take the n common, so here n under bracket 1, again n common, under bracket 1 plus 1 by n. Okay, n get cancel, apply limit as n tends to infinity. Okay, so limit as n tends to infinity, 1 upon infinity it becomes 0, so 1 upon 1 it is only 1. Okay, so whenever we put series 1 upon n, then we get the radius of convergence is 1. Okay, that means we have radius of a convergence for our series. Okay, so let's consider this is the radius of convergence 1. Okay, so this is the radius for our convergence of a point. Okay, so this is 1, so radius of a convergence of our series is this much only. Okay, there are some other points also where series is convergent. Okay, here we are thinking about series 1 upon n only. Okay, there are some other infinitely many series. You may take that maybe highlight some other properties too. Okay, so you may take this series. So I taken 1 by n as a series, so I got the radius of a convergence for 1 upon n is a 1. Okay, so the series which is convergent inside this circle. Okay, not the boundary and outside. Okay, so it is convergent inside here. Okay, that means when n which is equal to 1, series divergent. Okay, why divergent? Because on the boundary that series also divergent. Okay, n is 1, it is a divergent. Okay, and when we take n is a -1, okay, n is a -1, we'll get the series convergent. Why it is convergent? So -1 raised to n upon n, this series is always convergent. Okay, in its domain of interval. So here it seems like that series is convergent at n is equal to -1 and divergent at n is equal to 1. Okay, so that means the series which included point 1 but excluded point -1. Okay, sorry, which excluded point -1 included point +1. Okay, so here series is convergent on -1 but divergent on 1, so this interval is a convergent interval for our series. Okay, and can we say that this interval which belongs to open interval -1 1? Okay, Can we see that? Okay, so here -1 point, it lies here in this set, okay, but when it is not lying, okay, so this is the set, it is needed this way, okay. So this is convergent on this set, okay, this set which belongs to this set, that means our series is convergent on this particular set, okay. Now let us see the options here. So here I got the series is convergence, interval of convergence of our series is -1, open interval 1, okay. But as we can see, open interval -1 1, it is a subset of this interval, closed interval -1 1, okay. So if this is a subset of this interval, then we say that our option number 3, which is some set containing this containing here in some set, which is a convergence of our series, okay, interval of convergence of series. But in option number D, it is given open interval -1 1, okay. This is not possible, so option number 4 is discarded here, and option number 3, which is the correct over here, okay. I hope you all have understood my today's solution from real analysis. It's a very easy solution. Need to apply some of the conversion tests to get our options true or wrong, okay. Mostly in exam, you have to try to discard the option. You cannot make the option true. You have to try to discard the options, okay. I hope you all have understood my today's lecture. It is from CSIR NET paper 3rd question. It's quite easy. Nothing is difficult there. So within that, only 3 options. Option number 3rd is true. So even after, if you found anything difficult, let me know in comment section. I will come up with some other videos. So thank you everyone. Thanks for my today's lecture.